Hello, friends. Are you ready to revolutionize your deep learning game? Glowing Star dive into the world of MATLAB's Deep Network Designer, where complex neural networks become as easy as drag and drop. From extracting data to transfer learning and beyond, we've got you covered. Whether you're a seasoned pro or just starting out, this video will supercharge your AI skills and take your project. Contents. Introduction. Get started with Deep Network Designer. Extract data for training. 2. Select a pre-trained network. 3. Load dataset. 4. Edit network for transfer learning. Check network. 6. Train network. 7. Export results from training. 8. Test train network. 3. Conclusion. Introduction. Deep Learning Toolbox provides a framework for designing and implementing deep neural networks with algorithms, pre-trained models, and apps. You can use convolutional neural networks, CONVNets, CNNs, and long short-term memory, LSTM, networks to perform classification and regression on image, time series, and text data. You can build network architectures such as generative adversarial networks, GANs, and Siamese networks using automatic differentiation, custom training loops, and shared weights. With the Deep Network Designer app, you can design, analyze, and train networks graphically. The Experiment Manager app helps you manage multiple deep learning experiments, keep track of training parameters, analyze results, and compare code from different experiments. You can visualize layer activations and graphically monitor training progress. You can import networks and layer graphs from TensorFlow 2, TensorFlow Keras, and PyTorch, the ONNX, Open Neural Network Exchange, model format, and Caffe. You can also export deep learning toolbox networks and layer graphs to TensorFlow 2 and the ONNX model format. The toolbox supports transfer learning with DarkNet 53, ResNet 50, NASNet, SqueezeNet, and many other pre-trained models. You can speed up training on a single or multiple GPU workstation with Parallel Computing Toolbox, or scale up to clusters and clouds, including NVIDIA GPU Cloud and Amazon EC2 GPU instances, with MATLAB Parallel Serve. Get started with Deep Network Designer. In this video, we show how to use Deep Network Designer to adapt a pre-trained GlueNet network to classify a new collection of images. This process is called transfer learning and is usually much faster and easier than training a new network, because you can apply learned features to a new task using a smaller number of training images. To prepare a network for transfer learning interactively, use Deep Network Designer. Extract data for training. In the workspace, unzip the data. Unzip mergedata.zip. 2. Select a pre-trained network. As shown in the beside figure, select GlueNet. 3. Load dataset. To load the data into Deep Network Designer, on the Data tab, click Import Data, Import Image Classification Data. In the data source list, select Folder. Click Browse and select the extracted merged data folder. The dialog box also allows you to split the validation data from within the app. Divide the data into 70% training data and 30% validation data. Specify augmentation operations to perform on the training images. For this example, apply a random reflection in the x-axis, a random rotation from the range, -90, 90 degrees, and a random rescaling from the range, 1, 2. Click Import to import the data into Deep Network Designer. Using Deep Network Designer, you can visually inspect the distribution of the training and validation data in the Data tab. You can see that, in this example, there are 5 classes in the dataset. You can also view random observations from each class. Deep Network Designer resizes the images during training to match the network input size. To view the network input size, in the Designer tab, click the Image Input layer. This network has an input size of 224 by 224. 4. Edit network for transfer learning. To retrain a pre-trained network to classify new images, replace the last learnable layer and the final classification layer with new layers adapted to the new dataset. In GlueNet, these layers have the names Loss3, Classifier, and Output, respectively. In the Designer tab, drag a new fully connected layer from the layer library onto the canvas. Set output size to the number of classes in the new data, in this example, 5. Edit learning rates to learn faster in the new layers than in the transferred layers. Set weight learn rate factor and bias learn rate factor to 10. Delete the last fully connected layer and connect your new layer instead. Replace the output layer. Scroll to the end of the layer library and drag a new classification layer onto the canvas. Delete the original output layer and connect your new layer instead. Check network. Check your network by clicking Analyze. The network is ready for training if Deep Learning Network Analyzer reports 0 errors. 6. Train network. To train the network with the default settings, on the Training tab, click Train. If you want greater control over the training, click Training Options and choose the settings to train with. The default training options are better suited for large datasets. For small datasets, use smaller values for the mini-batch size and the validation frequency. For more information on selecting training options, see Training Options. For this example, set initial learn rate to 0.0001, max epochs to 8, and validation frequency to 5. As there are 55 observations, set mini-batch size to 11 to divide the training data evenly and ensure the whole training set is used during each epoch. Upper graph. This graph illustrates the accuracy of our model over time. The blue line represents training accuracy, showing how well the model performs on the data it has already seen. The orange line represents validation accuracy, which measures the model's performance on unseen data. As you can see, both lines generally trend upwards, indicating that the model is improving. Lower graph. This graph depicts the loss function over time. The loss function measures how well the model is predicting the correct output. Ideally, we want this value to decrease as training progresses. Both the training loss, blue, and validation loss, orange, are going down, which is a positive sign. Key metrics. Validation accuracy currently stands at 90%, which is quite good. This means our model is correctly classifying 90% of the data it hasn't seen before. Training time. The training took 34 seconds to complete, which is relatively fast. Epochs. We ran the model for 8 epochs, which means the entire dataset was processed 8 times. Iterations. Each epoch consisted of 40 iterations. Learning rate. The learning rate was set to a constant value of 0.0001, which determines the step size the model takes during optimization. Interpretation. Overall, the training process seems to be successful. The model is learning from the data and improving its accuracy while reducing the loss. However, it's important to note that these results can vary depending on the complexity of the problem, the dataset size, and the network architecture. Next steps. While these results are promising, further analysis is needed to fine-tune the model. We can experiment with different hyperparameters, such as the learning rate or the number of epochs, to potentially improve performance. 7. Export results from training. To export the results from training, on the Training tab, select Export, Export Train Network, and Results. Deep Network Designer exports the train network as the variable train network _1, and the training info as the variable train info struct _. You can also generate MATLAB code, which recreates the network and the training options used. On the Training tab, select Export, Generate Code for Training. 8. Test Train Network. Select a new image to classify using the train network. I=mred, mergedataTest.jpg. Resize the test image to match the network input size.
I=im resize. I 224224.
Classify the test image using the train network. Ypred, probs, equals classify, train network _1, I. Imshow I. Label equals ypred. Title, string, label, plus comma, plus number 2 str, 100 asterisk max, probs, 3, plus %. Then finally, as shown here, we predicted output as MathWorks Cube with 95.9% accuracy. Conclusion. In this presentation, we've explored the powerful capabilities of MATLAB's Deep Network Designer. We've walked through the process of extracting data for training, selecting a pre-trained network, loading a dataset, and editing the network for transfer learning. Additionally, we covered checking the network, training it, exporting the results, and testing the trained network. By leveraging these tools and techniques, you can accelerate your deep learning projects, ensuring more efficient and effective model development. The hands-on approach provided by Deep Network Designer simplifies the process, making advanced deep learning accessible even to those new to the field. Thank you for your attention, and I hope you now feel more equipped to utilize Deep Network Designer for your own deep learning applications.